Hello BookTube, this is Prometheus, and today you are going to enjoy the torture that I have been torturing myself with for a while. Now, I have been trying to figure out the internal combustion cycle for an auto engine, using the Keenan and K gas tables, and I ran into a couple of problems. Now, this is much better than the other version that I was trying to use, but there were still some underlying issues. So we can skip the first part of the example, which was from a thermodynamics book from the 60s, because it doesn't apply to what we're doing quite yet. So we started out with a compression ratio of 7.5. Now we need to find relative volume 2, in which case we take the relative volume, which is 58.58, and divide it by, where's 158.58, and we divide that by 7.5, and if I'm not mistaken, that should put us at approximately 2121, which has all of those wonderful numbers right there. So we increase their heat, pressure ratio, and then the pressure ratio, if I am not mistaken, is equivalent to 14 times, what was it? It was 20.051 over 1.2147. Alright, so this is very poorly written. And then that should equal approximately 231 psia. Alright? Everything's going well now. We figured out our T1, which is our intake temperature. We figured out T2, which is our compression temperature, and all the gas table doodads that come along with it. Now here's the problem. The example used in the book used a 0.0556 pounds of fuel per pound of air, which is approximately equal to a ratio of 18 pounds of air to 1 pound of fuel, which is very much, sorry for the glare, I do apologize for that. Here, let's see if, okay, hang on one second, I'll be right back. Okay, I got some room to move around here, okay. Still a little bit of a glare, but whatever. Sorry, people. So, we have this ratio right here. Now, this is on the very tail end of what can actually burn. So I wanted a more reasonable ratio used in aircraft engines, which is what I've been studying, of 11.5, which is pretty close to max power, which is what I want to study, is the max power. Now for this particular engine, which was an 0520, it has a rough max power of about 375 horsepower, so this equation should be getting that number. Granted, this is 100% volumetric efficient for this particular equation, so we'll need to get that sorted out after we finish it. But the problem is that we haven't quite gotten to that point yet, because 11.5 is equal to 0.0869, if I'm not mistaken. These numbers are off the top of my head. I have so many digits floating around in there, so that's probably not accurate. Please forgive me. Now, the problem is that in the example, we took this number, times it by the fuel rate, which was 0.0556. Now, theirs used 19,000 BTUs per pound of fuel. That's what they use. Now, I'm using 100 low lead, which is approximately 18,700 pounds of fuel. Why am I European all of a sudden? There we go. And then that is equal to QA. Now QA plus U2, which U is the energy of compression, should equal the energy of U3. Now this is what they did to discover T2. They found U3 and then they used that to find the temperature. Now this would be great, except that the scale ends at 6,500 Rankine. And I don't have any tabulated data beyond 6,500 Rankine. Whereas in this one, I add the heat from not 5.56, but 0.08, what, that number. And that number is much higher when added with wait, where's QA? There we go. QA plus U2 equals U3, which doesn't exist in the tabulated data. Well, Crud. What do I do now? Well, I can still figure out the temperature, right? Right? Hang on, let's erase all of this and get ourselves some room again, because you know what? Let's take a little walk, okay? Let's just go on a little walk. Oh my goodness, what's going on over here? I have no idea. And okay, yeah. So we're over here now. We can take QA, which would, or actually scratch that, Q3 or U3, which is the heat that we need to find, which is equal to the weight of charge, which is 1 pound currently. We times it by pounds at a later date, times CP times the change in temperature, which would be T3, which is the one we want to find out, minus T2, which was 1143 Rankine. Now this would seem simple enough, right? Now, if we add that all together, it was approximately 1824 BTU is equal to 0.24, don't know why I did that, times T3 minus 1143 Rankine. Alright, it's nice and simple. Do some cross multiplication. This is 0.24 plus 4311. Alright, and that should equal T3. Now, this worked, sorta, because it put out a temperature of 8,768 Rankine, or something close to that. Which, okay, that makes sense. That's much higher than the tabulated data. But I need, go back over here, I need pressure ratio and volume ratio. Now, as you can see, the numbers for this one, which used that aforementioned 0.55, it was 6, not 8, 0.556 of a pound, did land just barely in the table. Just barely. And as you can see here, the pressure ratio, it got kind of large. Hang on one sec. Alright, what was I talking about? Small distraction. Oh yes. So we have this temperature here. Now, we can take the temperature and divide it by the other temperature, which was 1143, times it by the initial temperature, which was 231. So those are degrees Rankine. That's the PSI from the other side. This was a decimal, but I'm just rounding because I'm trying to get across my issue. And then that should equal whatever the pressure is at the detonation, which, if I remember correctly, was, what was it, 1768? Alright, 1768 and 231. Now, if we go, we have an equation by which we can figure out the pressure ratios of these doodads. So if it was 17, ooh, that was pretty, 1768 divided by 1143, sorry, 231. Alright, and then that should be times that by the pressure at that, the pressure ratio, which, if we go over here onto the dark side of the whiteboard, was pressure ratio, or relative pressure, whatever it was, relative pressure, relative volume. Relative pressure was 20.051, and we times this by 20.051. It equals a number that I don't remember, but the point is that it's very, very low. It's somewhere in the hundreds, like 153 or something like that. Now, if we go over here and look at the actual numbers for the temperatures of something I could calculate, the pressure ratio was 16,000. And since the temperature has already exceeded the 6,500 scale, I would expect this to be at least in the 20,000s because that's where it ends on the tabulated data of King and K, Table 1. So this low number is confusing to me, and I don't understand why I keep getting it, because if I do the pressure 1 divided by pressure 2 is equal to the relative pressure of 1 divided by the relative pressure of 2. Now, I did this equation using the initial values, which was 14 psi divided by 231 psi, which was equal to the pressure ratio, which if you rewind the video real quick, looked like 1.147 divided by x. And then I put this into the calculator, or I put x here or x here, and guess what? It worked out this calculation no problem. But when I tried to change it so that 231 became that one, so 231 over 1768 equal to 20.051 over x, still produced that 153 number that we were getting earlier. So the temperature and the pressure ratios and the relative volumes are not working out. Now, supposedly, there was an equation. No, not supposedly. There was an equation which looked to figure out the relative pressure, you needed to equal the specific volume, which was 53.3, times this symbol over joule, which was 778, and this symbol was equal to this symbol 2 minus that symbol 1, which was equal to the integral of T1 over T2 0.24 over T as the derivative of T. Now my math didn't actually work out because I have no idea how any of this works, and this supposedly can put that out, and then once we have this, we can figure the relative volume, because it is equivalent to RT divided by PR. But I am currently stuck here, and I have no idea how to get past this point, and I've been banging my head into the wall with this for the last 17 hours, give or take, just on this problem. So if you happen to know where I'm going wrong, please comment. I would greatly appreciate the help. Thank you for enjoying this mad escapade. You think this guy ever had to worry about the internals? No, he didn't have to worry about that. He just said, go do it for the glory of the revolution. And this guy, he just didn't care. He thought they were all capitalist pigs. He didn't even bother with all this math stuff. He just said, build it. He didn't care if it worked. He probably did when his coffee machine kept burning his coffee. Can you believe that all of these people had no idea what drip coffee was? That we had to go to the moon without drip coffee. That to me is shocking. Thank you for watching.